All right, ladies and gentlemen, thank you for watching. This is Mark Anderson from Kellogg Community College, and we are going to be looking today at multiplying radicals. We're going to also divide radicals. We're also going to do some other things such as distribute radicals, like in FOIL or just normal distribution. We are going to clear the denominator and then kind of put everything together at the end in these rather quick examples here. We're going to kind of show you a lot of synergy from the rules we've been using earlier this week and in the previous videos. We're going to start off today with looking at the square root of 3 times the square root of 27. Now, because the product rule says that if you have the square root of a times the square root of b, you can combine them within the same radical here, as long as multiplication is involved. I can make this the square root of 3 times the square root of 7 into the square root of 81, which is quite nice because the square root of 81 is 9. And like in previous videos, I've mentioned that we sometimes look at the plus and minus values, especially when x's and y's are involved, but we are going to assume that everything was raised from a positive number, so we're not going to look at the plus or minus of any of these as we take the square roots. Well, at least not until the quadratic chapter, when we deal with more of the quadratic formula. So in problem 2, we're going to use the same principle here. We're going to combine this all under one radical and go x times x cubed. So x times y to the 5th times x cubed times y. If I combine all of these together and in these kind of like terms kind of feeling where I've got x times x cubed, which gives me x to the 4th, and I have y to the 5th times y, which gives me y to the 6th. What this does, it allows me to take the index of this problem, which is 2, and figure out how many times does 2 go into 4, and the answer there is 2. Or how many times does 2 go into 6, and the answer there is 3. Another way to look at that is that the index, or the square root, is actually the half power, and the half power of 4 is 2, or 4 to the 1, 4 times 1/2 is 2, and 6 times 1/2 is 3. A lot of different ways to kind of do these problems, and you should check out my previous videos where I go more in depth and explain this a lot more. But the third example here kind of wraps up our little short piece here about multiplying radicals because you can combine this into 36 because 2 times 18 is 36. X times x to the 5th is x to the 6th, and y to the 3rd times y is y to the 4th, which is pretty nice because we can now just take the square root of 36, which is 6. 2 fits into 6 3 times, or the half power of x to the 6th is x cubed. Or 2 fits into 4 twice, or, the 4th to the half power is y squared. So these three examples here are kind of basic, go over this principle of our product rule that we had for radicals. Now what we'll do is we're going to expand the product rule for radicals into this distribution problem. So the square root of 6 times the square root of 6 is 36, and the square root of 6 times the square root of 3 is 18. What we're about to do now is we're about to take our square root of 36 and we're going to get 6 out of that. And the square root of 18, I can break this into the square root of 9 times the square root of 2. And so this gives me 6 minus 3 square roots of 2. And this is the format I like it in. It's going to be rationals first and then irrationals next. I think this is a good order, and especially as we get closer to the quadratic formula, you'll see a lot of formatting that way. All right, continuing on with some other examples here to finish up this page. We're going to look at more kinds of FOIL and distribution here. Let's take a look at problem 5. We're going to have a distribution here where the square root of x times the square root of x is the square root of x squared. The square root of x times the square root of y is the square root of xy. Now this can be simplified because 2 fits into 2 once, or you can say x squared raised to the 1/2 power is just x, or you can think of it as where the square root and the power of the square, or x to the 2nd power, they can simplify to 1. Lots of different ways to think of it, and that is our final answer here. If I look at problem 6, do not distribute the 2 inside of that binomial, because that's not how that works. You have to write the problem twice and FOIL it. This will be our first FOIL problem using radicals, and you just want to take it slow and be careful. and I will show you the F, O, and I, and L step of FOIL, first outside, inside, last. So the first step here is to go 3 times 3, which is 9, and the square root of x and square root of x is the square root of x squared. So that's the F cable. Then we're going to do the O cable, which is going to be 3 square root of x times negative y, or negative 3y square root of x. And I like putting my rationals before my irrationals when I do the problem. Then if I go under this problem, I get negative 3y square roots of x. And then finally, we're going to have plus y squared, because negative y and negative y make a positive y squared. Now what I'll do is put all this together. So 9 square root of x squared is going to be 9x. Negative 3y, and this is kind of a common term problem because my common term is y square roots of x. So if I lose 3y square roots of x and another 3y square roots of x, I've lost 6y square roots of x plus y squared. And that gives me my final answer. Looking at FOIL here, taking one step at a time, very slowly, this is 6 square root of x squared. Take this very slowly, this is negative 10 y square root of x, and again putting my rationals before my irrationals. This is going to be negative 9 y, excuse me, almost put my square root there, y square root of x, and over here negative 15 y, excuse me, positive 15 y squared. Now let's do some simplification in the middle. The 6, or at first we're going to take the 6 square root of x squared and just make it 6x. If we lose 10, like this is our common term, y squared of x. So if we lose 10 y square roots of x and 9 y square roots of x, we get a total of negative 19 y square roots of x plus 15 y squared. And for problem 8, what we're going to do is do some more FOIL here, and we're going to take it very slow. We're going to have 2 square root of x squared. I'm going to take it over there, so we're going to have 4 square root of xy. Underside here, we're going to have 5 square root of xy. Let's use alphabetical order so we can see these as like terms here. And then minus the square root of y squared. So the first term is 20x. These two terms get combined, and I think I screwed up one of these here. Yep, that should be a minus. So I apologize for that. 4x, 4 square root of x times negative y is negative 4 square root of xy. I put plus, it should be a minus, so plus negative gets the job done. So if I have a negative 4 square root of xy and a positive 5 square root of xy, this leaves me with just 1 square root of xy, and we would not put the 1 in front of the xy. Don't put a 1 in front of here in your final answer. Just like 1x is technically not simplified. So again, don't do that. Then we're going to go minus the square root of y squared, which is going to be minus y. And that gives us our final answer in that problem. All right, so moving on to the next problem here, we are going to check out the third phase, which is looking at some quotients. And the quotient means, like just like in the product rule, the quotient rule is pretty straightforward. If you have the square root of a divided by the square root of b, the quotient rule says that you can combine them into the same radical. And this is true, for all division problems. I would strongly recommend you doing that if you can see a real simple way to get an easier answer. Like in this case, the square root of 50 over 2 is a lot easier than taking the 50, breaking it down, and then seeing if it simplifies with the square root of 2 in the denominator, which it does. This is just going to be the square root of 25, which is 5. And the same kind of easiness goes here if you just do some quick simplification, because 24 divided by 6 is going to be 4. And then x divided by x is 1. So you don't really put 1 over 1 there. And then what we have is y squared. So if we look at the square root with the index of 2, the square root of 4 is 2, and 2 fits into y squared once. So our answer for that problem is 2y. And that seems great. But now for part 3, you'll see that, or number 3, the problem I created here, has 4 parts to it. because now that we're kind of through our third phase of this lesson, where we've so far covered product rule, we've covered distribution and FOIL, and we've also in this last part talked about the quotient rule, now we get to talk about clearing the denominator. We cannot have a square root in the denominator. We can't leave our answer that way. So part 3a can't be left like this. You can't have 1 over square root of 6. So what you have to do is you have to multiply the denominator by something that will clear that radical out of the denominator. And for monomials in the square root, it's pretty easy, because since this is 6 to the 1/2 power, I'm going to multiply top and bottom by 6 to the 1/2 power, because 1/2 power plus 1/2 power is 1. What you really see, though, is that if I multiply the square root by itself, it gets the square root of 36, which is then simplifiable, like that. So square roots are pretty simple. You can memorize the idea of just taking your denominator and multiplying it by itself. If it's a monomial, it doesn't actually work for part C and D, as you will see. But for monomials in square roots, it's pretty straightforward. You multiply top and bottom by that radical in the denominator, and now I have 5 square root of x over x, like that, which is pretty straightforward, and you get the radical out of the denominator. But in part 3c, this is a binomial. You can't actually multiply the top and bottom by square root of 3, because then when you do your distribution, there'll still be a square root of 3 in the denominator. You can't multiply the top and bottom by square root of 3 minus 1, because it's just going to make a larger denominator. So what you have to do is you have to multiply by somewhat of a difference of squares technique. So take the binomial and multiply by that binomial. Instead of a minus, use a plus. Now what that's going to allow you to do is it's going to allow the denominator to actually simplify all of the radicals out of the problem. Now your numerator for this problem is pretty easy. I'm just going to write it down as square root of 3 plus 1, and I will change its order later. But let's now focus explicitly on the FOIL of the denominator. So there's square root of 3 times square root of 3, which is square root of 9. Here is square root of 3 times 1, which is square root of 3. Here is negative 1 times square root of 3, which is negative square root of 3. And here's negative 1 times 1, which is negative 1. So what this gives me is these two simplify to make 0. And this is square root of 9, which is 3. So my denominator is now 3 minus 1, which is 2. Wow, check that out. The denominator has no more radicals in it. The numerator, though, I would like to change its order. And I can do so just like that because it is an addition, and that means it fits the commutative property. So there's our answer, and for those of you who know what's coming up next, which is the quadratic formula chapter, it does kind of look like a quadratic formula answer, only if there was like a plus minus there. So we're getting there, we're getting there. All right, so here, following this pattern before, we're going to have to multiply the top and bottom by square root of a plus square root of b, instead of what you see down the denominator. Because if you do it that way, what you're going to get is a denominator free of radicals. Now up here, what we're going to have is the square root of a squared plus the square root of ab, which I can then change to a plus the square root of ab. Now let's actually look through the denominator and do our FOIL there. So this is going to be the square root of a squared. This is going to be positive square root of ab. This is going to be negative square root of ab, and this is going to be negative square root of b squared. So those go away, and that gives me the square root of a squared, which is a, minus the square root of b squared, which is b. So now I have a plus the square root of ab over a minus b. And notice my denominator does not have any more radicals in it. All right, so we got 4 more examples here. And this last phase is going to combine all the rules that we can combine together to make this problem easier or better, or I mean, really, it's the whole week in review if you started with my first video on a Monday. So what we're going to do here is look at the problem 4 and say, okay, it's a quotient, so maybe dividing is going to help me out here. So if I put this all under one radical, because I can do that using the quotient rule we learned at the top of this page, or problem number 1, we can go 32 divided by 2, and that's cool, that's 16. Now I have an x over x cubed, which means I'm going to have x squared in the denominator. And I'm going to have y to the 5th over y, so that makes y to the 4th in the numerator. So this is my new square root, combining everything in both radicals. The square root of 16 is 4. The index of 2, so 2 fits into y to the 4th 2 times. And 2 fits into x squared once. There you go. Okay, problem number 5. Problem number 5, I'm going to combine, since square root of 3 and square root of 3 are like common terms in the numerator, I'm going to combine them. So 3 square roots of 3, and this is using the addition and subtraction rules from the previous video. So 3 square root of 3 minus 6 square root of 3 is negative 3 square roots of 3 over square roots of 3. I don't actually need to rationalize this denominator because this just simplifies. Square root of 3 divided by square root of 3 is 1, so my answer is negative 3. But I will say that problem number 6 and 7, there is, when I teach this in class, there are usually one of two minds on this work. And the one mind is that, okay, we're going to clear the denominator here. And so we're going to multiply top and bottom by the square root of 32. Now what's going to happen here is the numbers are going to get pretty big, so you may want to have your graphing calculator or any kind of calculator with rooting capabilities out. Because as we multiply the top and bottom by 32, what's going to happen is that these numbers are going to get really big. And since the 32 is under the radical, 32 will only actually affect another radical and its size. So this is going to be 8x times the square root of 64 minus 3 times the square root, and this is 32 times 128, is 4,096. Now again, that is a very large radical there, but it does happen to work out pretty nicely in this problem. In the denominator, we have the square root of 32 times the square root of 32, which is either 32 squared or 1,024. Now, in my next step, if I just take the square roots of each of these under the radical, you will see that they work out to be pretty nice answers. This is 8x times 8. This is 3 times, just checking my work here, 3 times 64. And in the denominator, the 1,024 is 32, and that was not a big surprise because we multiplied 32 times 32, and then that would be the radical simplification there. All right, so with that in mind, we are now going to do some multiplication. So 8x times 8 is 64x minus, and these two multiplied together is going to give me 192, the 3 times the 64, and that's all going to be divided by 32. What's great about that is 32 is divisible by both of these numbers. So if I break this up into 64x over 32 minus 192 over 32, I can now divide this 2 to make 2x, and I can divide these two to make an answer of 6, because 32 fits into 192 6 times. So my answer is 2x minus 6. But this isn't the only way to do the problem. In fact, I want to show you another way to do number 6 that would use some different rules that we learned this week, but would still get to the same answer of 2x minus 6. So one way we can do it is we can look at breaking all of these down as far as we can go. So in this case, problem number, the second term here can be broken down into the square root of 64 times the square root of 2, which then the numerator would become 8x square roots of 2 minus 3 times 8 square roots of 2. All divided by square root of 32, which I can break that down into the square root of 16 and the square root of 2. So this becomes, instead of the square root of 16, square root of 2 in the denominator, 4 square roots of 2 in the denominator. So my numerator now is 8x square roots of 2 minus 3 times 8, 24 square roots of 2 divided by 4 square roots of 2. Okay, now the best way to proceed from here is to factor out a common term in the numerator. And in this case, the common term in the numerator would be 8 square roots of 2. So if I factor out 8 square roots of 2, and what that leaves me with is a x minus 3, my denominator has 4 square roots of 2. And what I can do is then just simplify. Dividing the square root of 2 and square root of 2 makes 1. Divide the 8 divided by 4 makes 2. That's 2x minus 3, or 2x minus 6, which is what we got in the previous example. Again, that's just one way of doing the problem, and you can choose which way would be better for you. I'm going to do the same thing with problem number 7. I'm going to show you 2 ways to solve it, and you can decide which way you would like to do it better on your homework or test or quiz. So if I look at problem number 7, the way that I looked at this before is maybe clearing the denominator with the square root of y. Now the square root of y is only going to enter into square roots, and it's not going to enter into any of the non-square roots. So my numerator is now 2y times the square root of y to the 4th minus the square root of y to the 4th, all over square root of y times square root of y, which is the square root of y squared. Now what I can do is go through and simplify these problems. So I got 2y, and this is going to be the square root of y, and I just wrote the index here if you're wondering why that 2 just showed up. 2 fits into 4 twice, so this is 2y times y squared minus, and here I go, 2 fits into 4 twice, y squared. All over the square root of y squared is just y. If I combine the numerator, I've got 2y cubed minus y squared, all divided by y. And I can rewrite that as 2y cubed minus y squared divided by y in both instances. So I'm going to get an answer of 2y squared minus y. And that's going to be my answer. And that's, again, one of 2 ways to do problem number 7. Let me show you the second way to do it, which will then end my video here. Another way to do the problem, instead of clearing the denominators, we can actually work it with the numerator and say, okay, we can break this numerator into the square root of y squared and y, and here the same thing, the square root of y squared and y. And the reason why I want to do that is because this will then factor out, or not factor out, but this will get out some extra y's in the numerator, and so what we'll have left is the square root of y. So this is 2y times y times square root of y. So because this that I just put in the box is really y square roots of y, minus y square roots of y. Because this in the second box here, indicated with a star, gives you y and then square roots of y, because the square root of y squared is just y. Sorry for that little drag there. Okay, divided by the square roots of y. So now let's go through and see what we can do here. So we've got 2y squared, because y times y is y squared, square roots of y, minus y, square roots of y, over square roots of y. In my numerator, I can factor out a negative y. So I'm going to move that in the front, and now in parentheses, I have 2y squared minus y, all over square root of y. Bam, bam, all done, because that is divisible, and that makes a 1. And 1 times 2 squared minus y is 2y squared minus y. And that's just another way to do problem 7. So you can see by just building up some of these simple rules, problems can get really complex. But with a little practice, you'll do fine through the work here. And I do appreciate watching this video, which had lots of phases and lots of parts in it. And again, thank you for watching.